All right. Well, we are at the top of the hour and ready to introduce our next presenters. So as I mentioned before we took our short break, next up we have two students from Clark Magnet High School. I want to point that out explicitly because all of you GIS professionals or college students studying GIS, look out. The high schoolers are coming up fast. I've been saying that for a long time. So I want to introduce Matthew and Gabriela from Clark Magnet High School. They'll be talking to us about their CTE mission CubeSats for surveying homeless populations in high-risk fire areas. So Matthew and Gabriela, take it away.
Okay, so my name is Gabriela Marcucci and his name is Matthew Keshishian. We are both seniors at Clark Magnet High School and are taking the Honors Environmental GIS class. So the CTE Mission CubeSat Challenge is a program created by the Department of Education to help students develop technical skills for careers in space and related industries. Our team was tasked to develop a proposal for a mission that only 5 other teams in the nation would receive funding to carry out. Our proposal was accepted. Living in Los Angeles, it's known that many issues are prevalent in this city, but homeless populations and wildfires are 2 of the biggest problems we face today. When fires do erupt, firefighters have to quickly locate and rescue homeless individuals from areas that are in the direct path of fires. As a result, our project took into account the homeless in LA and the amount of camps that are in wildfire risk areas. Our group compiled both the process we used and our results into a story map, which we're showing right now. Los Angeles City is home to thousands of people who are considered homeless and do not have easy access to any shelter to protect them against natural disasters. In addition, California is known to be a high-risk fire state with many devastating wildfires over the years. This being said, we came to the realization that there must be a portion of the homeless population that resides in these high-risk fire areas. Through this realization, we began our project to document homeless encampments within high-risk fire zones and determine if they are occupied or not by using infrared remote sensing.
So you can see here that we actually have a map that's showing where there have been wildfires in the LA County over the last 100 years. And when you interact with the map, you could actually click to see when these fires occurred. And you can also see the homeless population in this area. So you could see in this region of LA County, there was a total of 56,000 documented homeless people, and 3,000 of them, over 3,000 were veterans, and many were unaccompanied youth. So it's a very real issue that many of these homeless populations are in areas that are both dangerous to them and dangerous to their surroundings. And we decided to focus our project on detecting where these homeless encampments are situated and how we can help with the situation.
After determining our mission for this project, we set out to obtain a proof of concept. We wanted to be certain that the infrared camera would be capable of capturing the thermal images of homeless encampments. To do this, we equipped a drone with an infrared camera and flew it over the homeless encampments in the Ventura Willowberry Preserve. The flight was successful, and we were reassured that our camera would be able to pick up on any infrared signatures in the homeless encampments. A video of the infrared camera in action can be seen here.
So you can see that as soon as our thermal imagery was turned on, it turned the landscape from a black and gray into different shades of red, orange, and blue. And in those orange and red spots are where thermal images or thermal signatures were detected. And these thermal signatures would otherwise be completely undetectable by the naked eye. And that shows the importance of thermal imagery in conducting our reconnaissance. So we mapped our flight path of the drone using an app called Strava. And you can interact with, sorry about that. So we mapped our flight path using Strava, and you can actually interact with the map where you could see both the elevation of our drone and the GPS coordinates over the flight path. And this is a still image of our homeless encampment that was detected.
Since the reconnaissance flight was a success, we are ready to begin building our CubeSat. The components of our CubeSat were built and put together by our team, and the frame of the CubeSat was made by our project partners at Grace Brethren High School.
So you can see below, we have a few images of our students working on the CubeSat, and we actually split our CubeSat's work into teams. So we had teams working on the ground and flight stations. We had a team that worked on coding, and we also had our partners at Grace Brethren who provided us with a metal CubeSat frame. And this was really important in making our CubeSat more durable and more resistant to hostile environmental conditions, which will come into play later in our presentation.
Before conducting flight operations, we set out to determine a study site that was suited for our criteria and created a site suitability analysis, which can be seen below. To begin with, we wanted our study area to be within a 15-mile radius of Clark Magnet High School to keep commuting distances short. This was achieved by adding a 15-mile buffer radius around the school. Since our data must be collected from air, we wanted to take into consideration and map any FAA UAS controlled airspaces in our 15-mile buffer zone. Next, we mapped open spaces in which a drone or payload carrying device could fly and ruled out the open spaces which resided in controlled airspaces. After determining the open spaces in which we could fly, we determined which areas are considered to be moderate to high fire risk areas and defined any intersecting open spaces within wildfire risk areas. Running these geoprocesses identified the open spaces which met our criteria was shown in boxes.
So if we press explore here, we could actually see the step-by-step process we took in our site suitability analysis. So to start off, we put a pin on our high school, Clark Magnet High School, and this was our starting zone because it was somewhere that everyone on our team could commute from. And we created a 15-mile buffer zone around our pin. So basically any area within this circle was viable to us because it would be within driving range and convenient for all members of the team. So next we added a layer showing FAA UAS controlled airspaces. And this was going to be important because one of our options for launching our CubeSat was a drone, and you can't fly a drone within any of these areas that are covered by the squares. So if we were going to use that as our flight method, we were going to have to avoid them. So next we added a layer that mapped open spaces. So you could see these regions in green are areas where we could find somewhere that's flat and has a surrounding area that's actually suitable for a drone flight. So this would exclude anything like residential areas or densely forested areas. And these were basically just possible start spots for our flight. So next we ran a geoprocess that would exclude any of these open spaces within the controlled airspace. And you could see it drastically reduce the number of green squares in our map. So to make our map a bit more usable for our own project, we decided to add wildfire risk hexagons. So any area that's covered by a hexagon was determined to have a medium to high fire risk. And the darker the color of the hexagon, the higher the risk of fire. So similar to slide 5, we added another geoprocess that looked for overlap between open spaces and the wildfire risk areas. And the resulting hexagons show where those two layers overlapped. And finally, we looked for spaces that met all 3 criteria, as in they were not in restricted airspaces, they were in open space, and they were also in a moderate to high fire risk area. And this is what our site suitability analysis gave us.
Okay, so the Hansen Dam Recreation Area fit perfectly into our site suitability analysis, except that it was an FAA UAS controlled airspace. To solve this issue, we decided to utilize a weather balloon rather than a drone. After setting up the CubeSat and mounting on the balloon, we began our first flight. This flight took place on April 28th, 2021 at 5:30 p.m. The GPS on our CubeSat did not work properly, so we improvised and used an app called Strava to map the path of the balloon during this flight. In addition to the GPS issues, the operations were cut short due to heavy winds, which can be seen in this video.
So as we mentioned earlier, the durability of our CubeSat was very important because we knew we would be facing wind conditions like this. And the fact that our CubeSat components were able to stay firmly secured and the frame itself was able to stay together was thanks to our collaboration with our partners at Grace Brethren High School. So you can see here, we ended the flight early because the CubeSat was not able to get accurate readings with the constant movement due to wind. But we can also see the full launch beforehand here. So our balloon for our first flight was kept a relatively short distance from us because we wanted this to kind of be like our test run. And we wanted to see what the limitations would be. So there were some other considerations, as you heard Ms. Evans by say, there were snakes in the area as well. Thankfully, we didn't run into any of those during this flight. So our first flight actually ended up being a pretty good success, and we were able to get the proof of concept for our project. And even though some of our data was not entirely accurate because of the previously mentioned GPS failure, our first flight was widely considered a success by our team. So you can see the altitude we're at now was about the maximum we kept it. And we calculated the field of view that our balloon would be able to see from this height, which our maximum was about 60 feet above the ground. And we'll go to those calculations after our second flight. So these are pictures of our first flight during the flight week. So this was our maximum altitude, which we mentioned was 60 feet above the ground. And this is the map that was created using the Strava app. And because it was kind of on the spot and we didn't have time to make a full replacement for our GPS, we just walked we had one person walking directly underneath the balloon throughout its flight path to be able to track its position. Unfortunately, this means we couldn't get good elevation data, but we did get a good map of what our balloon is able to cover.
To further improve our data, we returned to the Hansen Dam Recreational Area for a second flight. We followed the same process as the last flight, but decided to attach a phone which was recording GPS coordinates on Strava to the CubeSat payload. This provided us with more accurate data of the flight path and GPS coordinates of each image. The second flight took place on May 7th, 2021 at 7:30 p.m. Surprisingly, during our second flight, a wildfire had started, which caused us to limit our flight time and elevation, as it may have interfered with any air support which was on hand to aid in the containment of the fire. And these two are pictures of the second launch on May 7th.
So you can see here, we actually had two different maps for our second flight. So we had one that was created by the Strava app, which I mentioned earlier, and one by our new GPS module. And this time, instead of following around the balloon, we actually attached a phone to the payload and had the app running. So we were able to get elevation data from both the GPS and the Strava app. And you can see, despite some variance between the two, they had the same general shape for our flight.
This map was created using the geoprocessed data from our second flight. The flight path is illustrated by the white line with yellow pins, and zooming in reveals 30 square foot tessellations on the map. The red squares on the map represent coordinates where thermal camera readings were at least 15% warmer than ambient temperatures, and these represent locations of homeless encampments.
So if we take a closer look at this map, you can see that the pins are points at which our camera was taking measurements, and these squares represent kind of a division of our flight area to separate them into where there were thermal readings and where there weren't. So you can see we have a few red squares here, and this is where our camera picked up a 15% higher temperature than ambient. And you can see we actually had quite a few readings throughout our flight path. And the way we determined which areas we were going to analyze is we actually did some calculations using trigonometry to find the approximate area that our camera could view. And we determined this to be close to 30 feet. So we created tessellations around our flight path with a 30-foot radius to turn into these squares.
These two pictures are pictures that we found, took while ground truthing our data and during our second flight. And this map is of the same flight, but displays the elevation change of our weather balloon during its flight. So the lighter the shade of purple, the lower the balloon was during its flight. This data helped us determine the distance our camera could see during different times in its flight, as we knew its FOV, which was 55 degrees.
So if we take a closer look, this is actually very similar to our previous map, but instead we just turned it three-dimensional. And you could, as mentioned before, the darker the shade of purple, the higher the elevation was. And you could see towards the end, we started to cycle back towards our starting point, and we actually had to lower the balloon because, as we mentioned, there was a wildfire and there was air support that was flying in, and we didn't want to distract them or get in their way. And despite the wildfire being a setback, it actually proves how important our project is because we saw what we were studying right in front of us, and it's something that happens very frequently. So to calculate the field of view, we knew that we had a 55-degree view from our camera based on the manufacturer's provided statistics. And we took 60 feet, which was the height that our camera reached in the first flight. And we created a triangle, which we then split into two. And then by using trigonometry, we were able to find that the camera could see an approximate radius of 31 feet. And this is the measurement we used to create those circular tessellations in our previous map. And these are some images of the fire that occurred during our second flight. And this was in its early stages, so it did get more severe after we had left, but it just shows what a devastating problem it is for the LA County. So despite the seeming success of our project, we were faced with a lot of difficulties throughout the process, and a major difficulty came with the components we chose. So our first problem was when we were trying to choose a thermal camera for our project, and we actually went through 4 different thermal cameras, and all of them were not viable for different reasons. Some of them had inaccurate readings and were unable to tell temperature differences correctly, and others had too low of a resolution to see from the height we were looking from. And we settled on the MLX 9640 camera, which was the one that we calculated the field of view for, and we also used in our final flight. And another module that gave us problems, which we mentioned earlier, was our GPS. So in our first flight, we used the GPS that was included with our Arduino, which was a Maker GPS shield, and it was unable to pick up a GPS signal through the heavily wooded area that we were flying in. And because of this, we switched to the Grove GPS module, which was specifically designed for areas with high-rise buildings that might block the signals. And despite it not being its intended use case, our GPS module ended up working the second time. And when we actually did our second flight, there was a failure and a success, because even though our GPS was now working, our Bluetooth low energy connection was struggling. So we were rarely receiving data at our ground station. But this is why we included a redundant data system, and we actually had an SD card that was on board the CubeSat, and we were able to retrieve it and retrieve all the GPS and thermal reading images to map.
So finally, this project can be very useful in improving safety for the both homeless and general populations of LA County. By using GIS, our group was able to solve the problem of being able to easily access the locations of homeless encampments and their population when a wildfire is started. Then we used an ArcGIS story map to share results with the Los Angeles Fire Department. The fire department can then use this information to move homeless people out of fire risk areas, thus reducing the risk of losing their homes and causing damage to nearby properties. Our map is publicly available and can also provide citizens with information about fire risks in areas they either live in or are looking to buy property in. We improve the safety for both homeless and general populations of LA County, and public safety officials benefit from knowing the data of homeless camps within high fire risk areas so that they can safely and efficiently evacuate the area when a fire occurs.
So thank you so much for your time. We really appreciate the invite as student presenters. It's an amazing opportunity that rarely comes up, and we just wanted to leave a bit of time at the end to take some additional questions. Thank you very much.
All right. Well, thank you both for your presentation, Matthew and Gabriela. Phenomenal work. And I was giving some of my colleagues a hard time that you actually used math and trigonometry, and I know students often ask when they're going through high school and college, why do I have to know all this math? Well, you just showed us. So great work. We do have a few questions from from various folks here. So let's get into a few of those. First off, was there somebody sponsoring this project for you, or was it just a straight up school project you did yourselves?
So it was a program that it was a challenge that we participated in. It was sponsored by the United States Department of Education. If that's the answer to the question.
Yeah, and originally we just submitted our project proposal, so we didn't actually have any cost involved in that. And the way that we ended up getting our funding is there was 5 national finalists, and those finalists were provided $5,000 to carry out their project proposal. And we actually only ended up using about $900 of that. So we have a lot left over to continue our CubeSat work with future classes.
Great. And another question somebody said is, I'm impressed by the fact that you built your own sensor system. Have you ever done anything like that before, or what resources did you use to learn how to do this?
So I've had experience with coding before, but I've never used the language that Arduino used, which was C#. And there was a lot of resources online, especially YouTube videos, that helped me kind of figure it out. But I think the most useful thing and my favorite thing about Arduino in general, which is why we used it as our sensor system, is that every single module and library has its own documentation. So no matter what you're working with, you can always find kind of a reference sheet that guides you through what the different commands are. And from there, it's just up to you how you're going to use those. So our 15% measure was something that wasn't provided by the manufacturer. That was something we determined by testing with the thermal camera at different distances. And we decided that 15% would give us an accurate enough estimate. But for the sensor system, engineering it was essentially plug and play, but it did take a lot of work to actually secure it to our payload in a way that would remain fixed. And that was what was a lot of our trial and error.
All right. And kind of a related question somebody posed is, how did you distinguish the thermal radiation your sensor picks up as being human generated versus, say, maybe an animal? Or how would you if you haven't?
Once we got our thermal readings, we actually went and ground truthed our thermal readings. So that was actually one of the images we had here. So once we got a hit in one of those areas, we would go by foot and see if there was anything actually there. And you could see that we did distinguish that at least two of our readings were homeless encampments, one of which is shown in this picture right here. So it does take some footwork, but it's a lot less work than it would take if we were to go and manually look at the whole area before we got the thermal readings.
Okay. Somebody just asked, did you have an adult with you when you did this?
Yes, we did. We had our teachers and our parents along with us.
Yeah, safety first. Another question. Did you work with any public agencies to do this project as far as data or access or anything else, or was this all you guys again?
Well, for our maps, we used resources that were already available on ArcGIS. So anything that was publicly available, we used, but we did not work with any specific agency. We just used whatever data was already out there for use.
Okay. And another question, a couple are coming in. Did you see any privacy issues coming up in doing remote sensing of people?
Okay, so we actually did consider this, and that's why we chose our flight location as somewhere that's public, because it's not illegal for you to take remote imagery of someone who is in a public space, especially if it's not actually taking pictures of them, because our camera was not taking pictures of the people. It was actually just taking thermal readings only. So that way our ground truthing was more just putting a point on a map rather than assigning a picture to what they are. And the picture we took for the story map, there was no one in the encampment at the time. The thermal signature that was detected was residual thermal energy inside the tents.
Okay, that's good stuff. Let's see, we have a couple other questions here. Adam asked, have you started using GIS in any of your other classes or projects as you've gotten into it?
I mean, for our school, we have a GIS pathway, and that's 3 years back-to-back classes that you take to kind of learn how to use GIS in different contexts. And me personally, I haven't used it in any other classes because there hasn't really been any use case for it, because my only science this year is physics and this class. So however, there is application that could be used in biology, and actually our teacher, Ms. Evans-Bai, was looking to move this project from our pathway into the biology class with some of the leftover funds. So that's some overlap that could exist between our projects.
All right. Well, last question, and maybe if you guys were on earlier, you've seen the slides go by. We're hiring in LA County for GIS people. What sort of interest do you guys have in future careers in GIS?
I personally am open to any kind of career. I don't have a specific career that I want yet. I love doing things that are very manual and helping out people and changing my community to be a better place.
I'm interested in both programming and cybersecurity, and those are both things that can be implemented at the GIS level. So for programming, we obviously have our ArcGIS web client, but ArcGIS Pro is also something that once you start to get into the details of it, then that's kind of a heavily technical program. And it's something that I want to work with more and get better at. And also I would like to work at a higher level with these maps and kind of work with fresh data. And as our previous question mentioned, with other agencies that have their own, that have data that's not publicly available, because I feel that's the work that's actually going to be something novel and something that hasn't been seen before.
All right. Well, we are at the end of our time. I want to thank you both on really impressive work. Again, I think you just scared a bunch of the GIS professionals out there about, high schoolers that are coming up quickly behind them. And so, great work. Keep it up. And thank you to also your school for offering these opportunities. I hope we'll see more schools, high schools, and throughout the county doing that going forward. So with that, we'll
Thank
take
you so much.
yeah, thank you. We'll take our break until the bottom of the hour, at which time we'll come back for our final presentation of the day that's actually built sort of related topically. We'll be hearing from about the use of drones and drone imagery in mapping. So we'll be back in 5 or 4 now, and then we'll see you then. Thanks.